Okay, in today's lecture, we're going to move on to the next part of the section 5.1 material on double integrals over rectangular regions. And in this part of the section, we're going to talk about something known as an iterated integral. So we saw, based off the definition of a double integral in terms of the limit of a double Riemann sum, well, it would be very difficult to evaluate these double integrals making use of that limit of a Riemann sum definition. So a much easier way to evaluate these double integrals, which we'll start using from this point forward, is to make use of something called an iterated integral, and these iterated integrals will make use of something called partial integration. So just like we had partial differentiation for functions of multiple variables, we can think about finding antiderivatives or integrals of these functions of more than one variable. So let's start by defining an iterated integral. So let's suppose that we have a function f of two variables, and it is integrable over some rectangle R, defined as AB cross CD. So here our x interval ranges from A to B and our y interval from C to D. So we would define an iterated integral of that function f over the rectangle R as either the following integral or this integral. So in this first iterated integral, we are integrating the function f of xy first with respect to y over the y interval from C to D, and then with respect to x over the x interval from A to B. So to evaluate this iterated integral, where we have the order dy dx, we are first going to integrate the function f of xy with respect to y over the y interval from C to D. So really this iterated integral means that we are first considering the integral of f of xy with respect to y from C to D, and whatever we get for this function, we will then integrate with respect to the variable x over the x interval from A to B. Now, similarly, we could look at this other iterated integral of the function f of xy, where we integrate with respect to x on the interval from A to B, and then integrate with respect to y over the interval from C to D. So this iterated integral, where we first have dx dy, means that we will first integrate the function with respect to x over the interval from A to B, and then with respect to y over the integral from C to D. So let's look at an example of evaluating some of these iterated integrals. In this next example, we're asked to evaluate each of these iterated integrals. And notice for this example that we're integrating the same function, x to the fourth minus y squared, over the same range of x and y values, just reversing which variable we integrate with respect to first, either first with respect to x and then y, or first with respect to y and then x. So let's look at this first one. We are asked to evaluate the iterated integral from 0 to 1 and from 1 to 2 of the function x to the fourth minus y squared dx and then dy. So we start by evaluating our inner integral, that is the one, or integrating our function with respect to x. So if we evaluate the antiderivative of the function with respect to x, we have x to the 5th over 5 minus, if we're treating y as a constant, y squared as a constant, and the antiderivative of any constant with respect to x is x times that constant, in this case y squared. And we're evaluating this expression from x equals 1 to 2. And whatever we get for this value, we will then integrate with respect to y. So let's see what we get by evaluating our antiderivative at the endpoints, x equals 1 and x equals 2. So here, if we substitute 2 into our antiderivative for x, we have 32 over 5 minus 2y squared. And then we subtract what we get when we plug in 1 for x, which would be a 1/5 minus y squared, but since we're subtracting that value, we would have a plus y squared, and we're then integrating with respect to y. So simplifying a little bit before we integrate, we have the integral from 0 to 1 of 31 over 5 minus y squared dy. So the antiderivative of this function is then 31 over 5 times y minus y cubed over 3. And we're evaluating from y equals 0 to 1. So when we substitute 1 in for y, we have 31 over 5 minus 1/3. And then when we substitute 0 in for y, we get 0. So we're subtracting 0. And this leaves us with 88 over 15 for this iterated integral. Now let's look at the other integral where we were reversing the order of integration, where we had the order dy dx. So to evaluate the integral from 1 to 2 and 0 to 1 of x to the 4th minus y squared in the order dy dx, we first integrate with respect to y, and then whatever we get, we will integrate with respect to x. So let's see what we get. For our outer integral, we have the integral from 1 to 2, and the antiderivative of our function with respect to y will be x to the 4th times y minus y cubed over 3. And we're evaluating first from y equals 0 to 1. And whatever we're left with, we will then integrate with respect to x. So substituting 1 in for y, we have the integral from 1 to 2 of x to the 4th minus 1/3. And when we substitute 0 in for y, we're left with 0. So we've got the following. And finding the antiderivative with respect to x, we then have x to the 5th over 5 minus x over 3, which we're evaluating from x equals 1 to 2. So when we substitute 2 for x, we have 32/5 minus 2/3. And then we subtract what we get when we evaluate at x equals 1, which would be 1/5 minus 1/3. So combining like terms, we're left with 31 over 5 minus 1/3, which again gives us 88 over 15. So we see from this first example involving iterated integrals that if we're integrating the same function over the same rectangle R, that we got the same result regardless of the order in which we integrated. So if we first integrated with respect to x and then with respect to y, or first with respect to y and then with respect to x, it didn't matter. We ended up with the same result in the end. So we might ask the question, well, is that always the case? And the following theorem gives us an answer to that question. It says, yes, these two iterated integrals will always be equal as long as our function f that we're integrating is continuous over our rectangle. So this result is known as Fubinis Theorem. And it says if our function f is continuous over the rectangle R, defined as AB cross CD, then the double integral of our function f over that rectangle is equal to the iterated integral of our function f in the order dy dx, or the integral of our function f in the order dx dy. So now that we have this result, let's look at another example of evaluating a double integral. We now have a way to evaluate these double integrals using iterated integrals rather than relying on the limit of a double Riemann sum. So here we're asked to evaluate the double integral of x times e to the xy dA over the rectangle R, which is defined as 0, 1 cross 0, 1. So here, we can integrate this double integral, making use of iterated integrals in either order, either first with respect to y or first with respect to x. So let's consider how we want to evaluate this. Here the function is x e to the xy. We're integrating with respect to area over the rectangle R. And we could evaluate this as an iterated integral, either from 0, 1 and 0, 1 of x e to the xy dy dx, or we could use the iterated integral 0, 1, 0, 1, x e to the xy dx dy. So it's up to us to choose which of these orders of integration we'd rather use. And in several of these problems, one of our orders of integration will result in a much easier antiderivative. So if we look at this first iterated integral, let's see how we could evaluate it. If we are first finding our antiderivative with respect to y of the function x e to the xy, we would have for our antiderivative x times e to the xy, and if we're integrating with respect to y, our antiderivative would then be this same function e to the xy divided by x, where we would evaluate from y equals 0 to 1, and then with respect to x. So we see here that our x terms on top and bottom cancel, and we're left with the integral from 0 to 1 of, if we evaluate e to the xy at y equals 1, we have e to the x, and we subtract what we get when we evaluate e to the xy at y equals 0, which would give us e to the 0, or 1. And then we would integrate with respect to x. So from here, it's pretty straightforward. Our antiderivative of this function would be e to the x minus x, which we evaluate from 0 to 1, which would leave us with e to the first minus 1, and then we subtract what we get when we plug in 0, which would be e to the 0 or 1 minus 0. So we're left with e minus 2 for the value of this double integral. Now, if we were to make use of this other iterated integral, where we first integrate with respect to x first, well, let's see what we would have to do. We would first be looking at the integral from 0 to 1 of x e to the xy with respect to x, and then integrating with respect to y. Now, to find an antiderivative of this function with respect to x, well, we see it's a product of functions involving x. We would have to make use of integration by parts. So we could choose u as x and dv as e to the xy dx, so that our du is dx, and v would be 1 over y e to the xy. And so we would have the integral from 0 to 1 of, using integration by parts, we would have x over y e to the xy evaluated from 0 to 1, minus the integral from 0 to 1 of 1 over y e to the xy dx, and then integrate this with respect to y. So we see pretty quickly that if we were to use the order dx dy to evaluate this double integral, we get an antiderivative which is much more difficult to evaluate. So in general, for these double integral problems where we make use of iterated integrals, it is always best to choose the order of integration that will result in a simpler integral. And depending on what type of function we're working with, we can see which order of integration would be the easiest to work with. So let's look at some other examples of evaluating these double integrals using iterated integrals. So in this next example, we are asked for the volume of the solid S, which lies underneath the plane, z equals 2x plus 4y plus 2, and above the rectangle R, defined as 0, 1 cross 1, 4. So we saw in the first part of this section that a double integral represents the volume of a solid underneath a function. So to get the volume of this solid that lies underneath our function and above the rectangle R, we would be evaluating the double integral of our function, which is 2x plus 4y plus 2, over the rectangle R. Now, to do this, we could use an iterated integral. So I've got a couple of choices. I could either integrate with respect to y first, so we would have the integral from 0 to 1 and from 1 to 4 of 2x plus 4y plus 2 in the order dy dx. So here, if we're integrating first with respect to y, well, the range of our y values was from 1 to 4, so that's the region we use for that inner integral. And then with respect to x, so our outer integral would have the x limits of integration from 0 to 1. Or if we wanted to, we could reverse that order of integration and go from 1 to 4 and 0 to 1 of 2x plus 4y plus 2 in the order dx dy. Now we see in this example that the function we're integrating is a polynomial with respect to x or y, so it doesn't appear that either one of these integrals would be any easier to evaluate than the other. It really doesn't matter what order we use here. So if we stick with the order of integrating first with respect to y, let's see what we get. So our outer integral is from 0 to 1, and the antiderivative of our function with respect to y will be 2xy plus 2y squared plus 2y, where we evaluate from y equals 1 to 4, and then integrate with respect to x. So let's see what we get for our inner value here. We've got the integral from 0 to 1 of, substituting 4 in for y, we have 8x plus 32 plus 8. And then we subtract what we get when we plug in 1 for y. So here we have 2x plus 2 plus 2. And we're then integrating with respect to x. So let's group like terms and see what we're left with. Here we go from 0 to 1. In grouping our x terms, well, we had an 8x minus 2x. So we're left with 6x. And then grouping our constant terms, we had a 32 plus 8, or 40, minus 4 leaves us 36. And we're integrating this with respect to x. So our antiderivative is then 3x squared plus 36x, evaluated from 0 to 1. So this leaves us with 3 plus 36 minus, when we plug in 0 for x, we get 0. So we're left with 39 for the value of this volume. 39 cubic units here, whatever our unit for measurement happens to be. Now, if we had evaluated the other integral with the order reversed, well, we know that this function z is continuous over our rectangle since it's a polynomial. So Fubinis Theorem says that we would get the exact same value of 39. So if you want to check, you can evaluate this other integral with the order reversed, and you'll see that you also get a value of 39. Okay, so in our last example for this section, we are again asked to find the volume of the solid S, which lies underneath a circular paraboloid defined by z equals x squared plus y squared, and lies above the rectangle R, defined as -2 to 2 cross -3 to 3. So we know that the volume of a solid that lies underneath some surface and above a rectangle is given by the double integral of that function, in this case x squared plus y squared, over the rectangle R. And to evaluate this double integral, we can make use of iterated integrals. So we could first integrate here, let's say going from -2 to 2, and then -3 to 3, the function x squared plus y squared. So this would be in the order dy dx, since our inner integral had limits of -3 to 3, that is the value of our y interval. Or we could reverse this order, and we would be integrating from -3 to 3 and -2 to 2, the function x squared plus y squared dx dy. Now, again, in this example, the function that we're integrating is a polynomial function, so there's really no benefit to using one order over the other. It'd be equally easy to integrate in any order. So let me stick with the first order of dy dx. So here, one thing that we could make use of to make this problem a little bit easier is the symmetry of our solid. So rather than integrate over this full rectangular region, if we visualize our solid, we see that it's symmetric about the x and y axes. So below, let's look at the graph of our surface. Here in the three-dimensional coordinate system, let's define our coordinate axes, x, y, and z. And we're integrating over a rectangle where x ranges from -2 to +2, and y ranges from -3 to 3. So the rectangle that we're integrating over would be the rectangle shown here in the xy plane. Now, the function that we're integrating is z equals x squared plus y squared, which in the problem we're told is a circular paraboloid. So it is a paraboloid opening upward from the xy plane with vertex at the origin, and the cross sections of this paraboloid are circles. So we see that this paraboloid is symmetric about the x and y axis. So rather than integrate over the full rectangle, we could integrate just over this part of our rectangle that lies in the first quadrant, where x ranges from 0 to 2 and y ranges from 0 to 3. And whatever I get for that result, I could then multiply by 4 to get the total value of my volume over that first region on which I integrated in addition to these other 3 quadrants. So to save ourselves a little work here, making use of symmetry of our region, we could say, well, let's take 4 times the integral over our rectangle in the first quadrant. That would be from 0 to 2 and from 0 to 3, the function x squared plus y squared in the order dy dx. So if we were to evaluate our integral with respect to y, we would have x squared y plus y cubed over 3, and we're evaluating from y equals 0 to 3, and then integrating with respect to x. So we have 4 times the integral from 0 to 2 of, if we evaluate at y equals 3, we have 3x squared plus 9, minus, when we evaluate at 0 for y, we have 0. And we're then integrating with respect to x. So we have 4 times the antiderivative of our function with respect to x is x cubed plus 9x, which we're then evaluating from 0 to 2. So this gives us 4 times 8 plus 18 minus, when we plug in 0, we get 0. So we're left with 4 times 26, which leaves us with 104 for the volume of this region. So in this last example, we see if we're trying to find the volume of some solid region which has symmetry, say over our rectangle,